Good morning, dragons, and welcome to another mini lesson. The other day we worked on solving one-step subtraction and addition equations. Now we're moving into the multiplication and division world. I'm actually going to skip over the warm-up and the getting started because I really want to get to the core of the lesson, which is using the bar model for multiplication equations. Now, when we did addition, I did a 3 color-coded model. So if you have crayons or colored pencils or anything you'd like to join me, I'm going to do the red, blue, green again. And I'm going to walk you through how to model these equations. Just as with addition equations, solving multiplication equations involves determining the value for the variable that makes the statement true. Remember, when it's an equation, you want to make the statement true with the value of the variable. You can use bar models to understand the structure of the equation and to reason about the solution. So, some important vocabulary in there. We want to make the statement true. We're working with bar models, and we're working with equations. Okay, here's a great example. Consider the multiplication equation 2x equals 6. Right, they've got us started here, so this is like 2x and 6 relates to this 2x and this 6. Notice that the bars are similar to when we did addition. They are of equal size, trying to show that they are worth the exact same value. This equation states that for some value of x, the expression 2x is equal to 6. Remember that an equation is composed of 2 expressions. It's just a little side note in case you forgot. An equation contains 2 expressions. You can decompose 2x by writing it as the equivalent expression 1x plus 1x, which is the same as x plus x. What are they trying to tell us? We decomposed in addition, well, we're going to decompose again in multiplication. So from here to here, it's like they chopped up the box. They decomposed. 2x is the same as x plus x. To maintain equivalence, decompose 6 in a similar way. Well, I want you to notice that we decompose 2x into 2 boxes, 2 equal boxes. So I need to decompose 6. Decompose 6 into 2 equal boxes. In this particular one, I don't even feel like I'm going to use my green pencil like I did in addition because I don't have much of a constant going on. I have a variable here and a variable here, and those variables match up with these solutions here and here. So this would still be the blue. This has not changed. But one of these boxes is not a constant like it was in addition. They're both variables. So these are both the solution for x. So now they've taken the bar model and put it into 2 equations that are equivalent. 2x, this guy, just became x plus x. It broke up into 2 parts. And 6, this guy, also broke up into 2 equal parts. Now, if you examine the structure of the second equation, you can see that one of the x's is worth 3. Because by default, the other x is also worth 3. Now, if you have any questions regarding this, remember to hold your questions until we meet on Zoom. Maybe write a note on your paper right now, or get a Post-it note or an index card and make some notes for yourself so that you'll be prepared during your Zoom meeting. Okay, let's take a look at number 1 together. Why is the number 6 decomposed, nice vocabulary word, into the numeric expression 3 plus 3? Notice they did not call it an algebraic expression. It is not algebraic because they took out the x's. The number 6 is decomposed into the numeric expression 3 plus 3 to mirror the structure of the expression x plus x. The number 6 is decomposed into the numeric expression 3 plus 3 to mirror the structure of the expression x plus x. What are they saying? They are saying they wanted this to look like this. They wanted the red to look like the red, like the same boxes cut up in the same way. They want it to be a match. They want x plus x to look like 3 plus 3. That's what they're looking for there. All right, you're doing excellent. Keep going. We're going to solve each equation using the bar model. Now, you won't do this forever. I don't want you to think that every time we solve multiplication equations, we're going to use a bar model forever and ever and ever. We start with the bar model so we can visually understand the mathematical concept. So let's start with number 1 here. And I want to start with the 2 original expressions. I want to say that all of 3x is worth 12. I want that to be true. So if I'm the original, I'm the blue. I've been doing my originals in blue. Okay, so we've got 2 lovely expressions in 2 equal-sized bars. Now I need to break up 3x because I want to get x to live alone. I don't need to know so much what all 3 x's are worth. They actually told me that. I need to know what just 1 x is worth. How do we do that? We create another bar. And think for a second. How many sections should you split this up into in order to have an x live by itself? If you reasoned 3 sections, you reasoned correctly. I need an x, and an x, and an x. I've got a series of variables. Now, if I did that to 3x, if I decomposed from here to here, I decomposed, and I decomposed into 3 equal-sized boxes, I need to do the same thing from here to the next thing I draw. So think about what your next bar is going to look like. What is it going to look like? Again, the bar itself is equal size to the original bars. From this step to this step, you chopped your bar up into 3 parts because you wanted x to live alone. So essentially, you divided 3x into 3 parts. Well, now I need to divide 12 into 3 equal parts. Well, 12 divided into 3 equal parts is how much per part? If you said 4, you are correct. So that pretty much tells me that 1x is worth 4. 2 x's would be worth 8. And we know all 3 x's is worth 12. What does this look like using the algebraic and numeric expressions together without the model? You start with 3x equals 12. You decompose 3x to be x plus x equal to 4 plus 4 plus 4. And from that, you can see that just one of the x's is equal to 4. The model is super cool. It really shows you why the math works. Take a minute, pause the video. Work on only 3 and 4. After you're done, come back and make sure you got the right solutions with me. We want to get the correct solutions. Okay, take a moment and pause now. Okay, hopefully you took a moment to attempt 3 and 4 independently. I'm going to illustrate them for you now. We know that the bar 7x, I'm going to draw this a little longer because 7x sounds really big, is going to be worth all of 63. I need to decompose 7x so that somewhere an x lives alone. I'm going to decompose 7x into x plus x repeatedly until I have 7 of them. I got to try to plan this out pretty good here. That's 3, 4, 5. Okay. 1, 2, 3, 4, 5, 6, 7. Okay, we got x plus x plus x plus x plus x plus x plus x. We've got 7 of them. Now, we have to do the same decomposition in the same manner for 63. Okay, not bad. So if we were to decompose 7x, from here to here we decomposed into 7 pieces. I need to decompose 63 into 7 equal pieces. What is 63 divided into 7 equal pieces? If you said 9, you are correct. So recapping, my original equation was the expression 7x is equal to 63. Once I decomposed it appropriately, I could see that 1x was the same as 9. 1x was the same as 9. All of the x's, all 7 of them, was equals to 7 nines, which is the same as 63. Using numbers only, we started off with 7x equals 63. We decompose that to be x plus x plus x to be 9 plus 9 plus 9 and so on. 1, 2, 3, 4, 5, 6, 7. And by analyzing the structure, we can see that one of these x's is equal to one of these 9s. Excellent. We're almost finished. Just one more. 4x equals 6. I start with two equal sized boxes. Expression 4x goes here. Numeric expression 6 goes here. I need to decompose 4x. I'm going to decompose it into 4 equal parts. Well, if I decompose that into 4 equal parts, I need to decompose 6 into 4 equal parts. That feels like a decimal or fraction in my mind right now. Let's see if that's true. What is 6 divided by 4? What is 6 divided by 4? I believe it to be 1.5. 1.5, 1.5, 1.5, 1.5. You could use a fraction here. I'm okay with that too. So we decomposed from here to here. Why did we choose the structure that we chose? We chose it because we want x's to live alone. We're trying to isolate an x. So we decomposed here. The character today is really in my way. We decomposed here in a likewise fashion, trying to be fair. You always want to be fair across the equal sign because both sides are currently sharing the same value, and if you mess that up, then it's no longer equal. Your original equation contained the two expressions, 4x and 6. After you decomposed it, you could visualize that one of the x's is worth 1.5. All of the x's, all 4 of them, is worth 6. The models are kind of fun. Math only, what does that look like? I'm going to try to squeeze this in. You know what? I'm going to squeeze it in over in the corner here, under his feet. We've got 4x equals 6. That became x plus x plus x plus x equals 1.5 plus 1.5 plus 1.5 plus 1.5. Sorry, I fell off there. And we can analyze the structure of the new equation, the equivalent equation, to see that 1x is equal to 1.5. Alright, so hopefully you felt some confidence with the model. The models are very interesting and they really do help with the concrete understanding of the entire process. There are shortcuts that I can teach you later, but if you understand how the model works, your brain will forever understand why it works. Thank you for joining me, and I'll see you soon in a live session.